Okay. So next couple classes moving into vectors. I've likely seen vectors in some other class, such as if you've taken a physics class. And operations on vectors are going to be important in Cal 4 for those of you who have to take that. Because one of the key topics in Cal 4 is vector calculus. So a lot of what we're covering towards the rest of the semester is meant to prepare you for that. Okay. So what is a vector? It could be a lot of things actually, but quantity that has two key properties: magnitude and direction. We're saying that makes me think of a first Despicable Me movie where the villain, whose name is Vector, talks about how his crimes have magnitude and direction. Yeah. So, unpredictable. Yeah, so that one would make me think of. Now, first, I'm going to talk about how you work with vectors in a geometric sense. So I'll be drawing a bit, and then how to work with them algebraically, which might be what you prefer. Okay, so, and we're concerned about vectors in two-dimensional or three-dimensional space. So a vector has an initial point and a terminal point. So the vector is what takes you from one point to the other. Right. Now, what that means is, and I'm trying to draw a scale as best I can. If I draw another vector over here, so that's a different initial point. And also a different terminal point. Okay. Stopping here. So these right here, the extent that I've drawn them properly, are actually meant to be the same vector. So because it's what's happening between the points that matters. So it may have different initial terminal points, but if how you get from one point to the other is along the same direction and the same length, same magnitude. So in fact, this length right here, vectors this time, the magnitude that I'm referring to is simply the length. The distance between the initial and terminal point. So same direction, same magnitude, we think of them as the same vector. And looking at my picture now, I really thought they were parallel. Whoops. Try that again. Wow. Don't use technology for anything. We can't do anything by hand anymore. It's meant to be the same dang arrow. Okay, just translated. Okay. Now, there are two key operations that we will perform on vectors. Okay. So the first is addition of vectors. So I can show you how you do that geometrically first, and then algebraically later. So what you do is, if I have, here's a vector I'll indicate by U. Now, in the notes, I'll indicate vectors by bold letters, but it's a little hard to do bold on a blackboard. So I'll use the arrow symbol to indicate a vector. And then here's another vector I'll call V. So what I want to do is add these two vectors together. Now, I can translate a vector to any position I want, and it's still the same vector. So I'm going to do that here. To show you how to get the sum of U and V. So I'm going to draw U again. And then I'm going to move V so that the initial point of V is same as the terminal point of U. So I'm going to start V right here. Okay. So now, visually, it's easy to explain how to get the sum. The sum has the initial point of U and the terminal point of V. So this vector right here is U plus V. You can also think of it as completing the triangle that U and V make. Okay. And this process of adding vectors is referred to as a triangle law. Now, I'm going to reproduce this down here with less clutter. All right, so here's U, V, and U plus V. But now suppose I want to add them in the opposite order, V plus U. So if I start at the same initial point for U, that's also the initial point of U plus V, and I draw V starting from that point. So here's V again. And then I add U to it. So I place the initial point of U at the terminal point of V. I draw U in. Again, it's supposed to be parallel, but of course I missed the mark. Okay. So this is V plus U, and we see that they're the same vector, which is what you'd expect, because generally speaking, addition should be commutative. And that's true for vectors, just as it's true of numbers. Okay, and the fact that these two vectors coincide, doesn't matter which order you add them. That is called the parallelogram law. It says that U plus V is equal to V plus U. And that's supposed to be a parallelogram. It's just drawn badly. Whatever. I give up. Okay. So question so far about vector addition. Now the second operation is scalar multiplication. So we don't have an actual vector multiplication operation. There are some products involving vectors that we'll see later. What we're talking about here is different. This is taking a vector U and multiplying it by a scalar, that's just the number. I refer to it as a scalar because of what it's being used for. It's to scale the vector u. Okay. But a lot of times people use number and scalar interchangeably. Especially what's important to distinguish like numbers from vectors. So here's my vector u. So this would be the vector 2u. It's a vector that is pointing in the same direction, but it's supposed to be twice as long. So if you're multiplying a vector by a positive number that's greater than 0, vectors pointing in the same direction, but the length or magnitude is multiplied by s. Okay. Whereas if I draw this vector that's pointing in this direction, that's a minus u. So if s is negative, that is pointing in the opposite directions. So either way, the length is scaled by the absolute value of s. And so that's how you visually depict scaling a vector. Now, if I take these two operations and put them together, I can pretty much define a number one. But these are the two fundamental operations that whatever kind of vector you have, you should be able to do. Add them and multiply them by numbers. But I could put these two operations together to define what it means to subtract vectors. So u minus v would be the same as u plus the vector minus v. So I can show you what that means. So here's vector u. Here's my vector v. So the first thing I do to compute u minus v is I negate v. So if that's v, then this, well, then this is minus v, just pointing in the opposite direction. And then I'll add u and minus v together. So now I have, here's u, and then I have minus v, and then I complete the same addition process. You complete the triangle, and that's u minus v. Whereas if I go the other way, there's the original v, and here I have u plus v. Now, if I have my vector u again, then I add to it minus u. And really these vectors are sitting on top of each other, but it's hard to distinguish that way. Then it brings it back. So u takes me from its initial point to its terminal point, and now I'm back to the initial point. So u plus minus u. That's a vector that has no magnitude whatsoever. So that's the zero vector. A zero vector doesn't have any well-defined direction, because you would be able to determine the vector direction unless it had at least some length to it. So it's magnitude 0. So with vector addition, just as we do have with addition of numbers, you have the notion of an additive inverse. So that's minus u. And then you have an additive identity element, 0. So you can add 0 vector to any other vector and it gives you the same vector. Questions so far? Okay. So having these operations leads to what's called a vector space. So so the vector space, which I'm using letter capital V to refer to, and what does it consist of? It consists of a set of vectors of some kind. And the two fundamental operations that you can form on them, so addition and scalar multiplication. But these operations have to satisfy, they have to possess these properties. The kind of properties that you would expect from addition and multiplication. Okay. All right. So for any vectors in your space, u, v, w, in the vector space, and also any scalars, c and e, that are real numbers. We have these laws that have to be followed. Again, there are really no surprises here. Vector addition must be commutative, as I mentioned, the parallelogram law. Plus v must equal v plus u. What's another property that addition of numbers has that we'd expect to carry over here?
Associated.
Yes, that's actually the next one on my list. So if I have 3 vectors that I'm adding, it doesn't matter if I add the first 2 and then add the third, or if I add the second and third ones and then add the first one onto the sum. The result will be the same. What's another property of addition? That applies to numbers. Okay. Identity element. Oh, yeah, it is a lot of the same thing, yeah. Yeah, I was about to invoke that, I figured, not many people appreciate that, yeah. Zero vector is the identity element, so any vector u plus the zero vector is u again. Okay, what goes with identity? Yes, we have, and I mentioned that earlier, additive inverse. U plus the negation of u must be the zero vector. Unfortunately, I still have a, oh, okay. I have a few more properties. Getting to one for scalar multiplication now. Yeah, okay, those are ones for addition. The ones that apply to scalar multiplication are, okay, we have a couple of distributive properties. So if I take a scalar c and scaling a sum of vectors, that's the same as scaling each vector individually and then adding those together. Now here we have distribution over a sum of vectors, but you can also have same thing or distributing over a sum of scalars. If I have two scalars c plus d times the vector u, that's the same as scaling u by each scalar individually and adding those up. So. Associativity for, so these are distributive. And then we have associativity again for scalar multiplication. So if I take a vector u and scale it by a product, CD, that's the same as scaling u first by d and then scaling that by c. So multiplying the numbers versus scaling the vector, you can do those operations in either order. And then finally, we have identity for scalar multiplication. So the number 1 times u is u. Okay. So 1 is the identity element for scalar multiplication. Must be an 8. All right. Okay. And now the only property that I find actually interesting is closure. Same, I mean, yeah, the same meaning that's in group theories. That if you have two vectors u and v that are in the vector space, their sum must also lie in the vector space. And any scaling of a vector must also be in the space. So for example, if I think of the set of vectors that have length 1, that's not a vector, that set of vectors is not a vector space. Because if I take a vector that has length 1 and I scale it by anything other than 1, that's going to take me outside the set. If you're defining a set of vectors that has certain properties, that doesn't necessarily constitute a vector space because it may not satisfy this closure property. Okay. Now, in this class, we're only going to be dealing with a couple of vector spaces. Vector space for vectors in 2 dimensions and 3 dimensions. But you can have different kinds of objects or entities that can be thought of as vectors. For example, set of all continuous polynomials would be one, or even more general, continuous functions, because if you take polynomials up to a certain degree, for example, if you add any two such polynomials, that's still a polynomial. And we certainly know how to scale polynomials. You multiply them by some number that will also have that degree or less. Yes, it's based on all continuous functions on a certain domain, because if you add two continuous functions, the sum is continuous. They have this closure property, and we certainly know how to add functions or scale functions by number. So there's different kinds of vector spaces. Now we're going to stay pretty limited in this class, but depending on what math classes you take, you may see our vector spaces. Well, I think actually in linear algebra, some of our vector spaces might come up. Yeah.
On the second to last line, what does the first like three characters? So you said a plus in between them?
Here,
No, there, yeah.
that's comma. Yeah, so U and V belong to the vector space. Yeah. Right. Okay, any questions up to this point? It's all rather abstract, but then now I can make things more concrete, because we're gonna now look at vectors in terms, describe vectors in terms of components. And that will enable us to work with vectors in an algebraic manner instead of the geometric that you've seen. And either perspective certainly can be helpful. Now, let me clear up my notation here. A point in three-dimensional space, I can indicate using parentheses. So U1, U2, U3 are the X, Y, and Z coordinates or components of a point in three-dimensional space. Or if we're only two dimensions, we're just going to have X and Y. By contrast, a vector in B3 is the set of all vectors in three-dimensional space. The value use these angle brackets instead of parentheses. So these are the X, Y, and Z components of the vector.
I think the word point does it say in?
Yes, point in R3. Now, Both vector B has the initial points, call it P1, that has coordinates x1, y1, z1. Okay. And then it has the terminal points, P2, that has coordinates x2, y2, z2. Then I can use that. Let's see. The vector B must be written this way as the vector that goes from P1 to P2, but the components of the vector, again, watch, I'm using angle brackets now, is the difference of the coordinates. So x2 minus x1 is the x component. Y2 minus y1 is the y component. Z2 minus z1 is the z component. So it's the difference between them that using the components of the vector. Now, if the initial point is the origin, use capital O, that'd be 0, 0, 0, then V would have, the V would be equal to the terminal point, or its components. And that is referred to as a position vector. In that case, where how we're interpreting the vectors is locating a point in three-dimensional space. So a vector goes from the origin to that point. All right, so as an example, I'm going to give you two vectors. U is a vector that goes from initial point U1 to terminal point U2. U1 is the point, is the origin. And U2 is a point 2, 3, 4. So if we subtract these, then U is a vector with components 2, 3, 4 that happen to match the coordinates of the terminal point because the initial point is the origin. So this U is an example of a position vector. That's how it's interpreted anyway. But now here's a second vector, V, that is vector from initial point V1 to terminal point V2. And V1 is a point 1, 2, minus 1. And V2 is a point 3, 6, 3. So if I subtract the coordinates of the terminal point and the initial point to get the components of V, I end up with 2, 3, 4. Same vector. Now, they may be interpreted differently because, for instance, U is a position vector while V is not, but U and V have the same magnitude. They have the same direction. we can say that U is equal to V because they have all the same components. Yeah, 1, 2, -1. Yeah. Oh, whoops, something's wrong. Oh, my notes are wrong. Dang it. Okay. That should be a 5. Okay. Wow. This Jake's been there since 2009. In other words, it's the first Cal 3 class I've had that's been paying attention. So good on you. All right. Okay, dang it. Okay. So again, even though the vectors may have different initial terminal points, we don't use those to determine whether two vectors are equal or not. It's all about the same magnitude, same direction, which is the same as checking whether they have the same components, which comes from subtracting their initial and terminal points. Okay. All right, and I mentioned magnitude a number of times. Tell you how to get it. So the magnitude or length of a vector v, which has components v1, v2, v3, is the following. Now, there's different ways of writing a magnitude. Like the first calculus book I was using here, used an absolute value to indicate magnitude of a vector. Like you'll be seeing the homework, and actually the notation I most often like to use is the double bar. To indicate magnitude of a vector. And it is a generalization of a notion of absolute value of a number. So it's not unreasonable to use absolute value as long as it's clear what you're taking the magnitude of. But how you compute it is the sum of squares. Square root of the sum of squares of all the components of a vector. Another way of putting it, if V is the vector from this initial point to this terminal point, so from P1 to P2, we can also say that magnitude of V is the distance from P1 to P2 using the distance formula that I gave you last time, and that would give you that same. What?
It looks like the.
Oh, this also means magnitude. It's just an alternative notation that some books use. I've also seen it in your homework problems. But then when you throw it off, when you see that.
It's just notation wise. Absolute value stands for like the length. Let's say order of a group.
Oh,
Like, is it just something general thing?
I guess you could say it's a symbol that's used in way too many contexts.
Yes.
Because it also means a cardinality of a set, which is closest to the meaning of it if you're thinking of for order of a group.
Yeah.
I guess it's always used to convey size of something or magnitude. So it's, but what does that mean?
Okay.
So, yeah.
Yeah, depending on the font.
Yeah. Okay. All right, so example for vector magnitudes. Okay, so if I have vector v, which goes from initial point P1 to terminal point P2, and P1, the initial point is -3, 4 minus 1. And then the terminal point is 1, 5, 0. Then the magnitude of b, square root of the sum of squares of the components of b, but you get that from subtracting these coordinates. So I'd have 1 minus 3 for x, then 5 minus 4 for y, don't forget to square them, and then 0 minus 1 squared for the z component. So we have 4 squared, 1 squared, 1 squared. So we end up with the square root of 18. That's what. So because vector magnitude involves a square root, the numbers are not always going to work out nicely. So that's something to keep in mind. Don't expect it. Okay. All right. So now we see how to get the magnitude of a vector in terms of its components. Now, what about the other operations we've already seen? Addition, scalar multiplication. We should be able to carry out those operations in terms of the components too. And fortunately, that is quite straightforward. So for addition, if you have a vector u that has components u1, u2, u3, v is a vector with components v1, v2, and v3, then the sum, you just add up the components. u1 plus v1 is the x component. u2 plus v2 is a y component. u3 plus v3 is a z component. So you just add corresponding components to get the components of the sum. Similarly, if I want to scale the vector u, that just means scaling the components. Okay. So example, suppose that the vector u is 7 minus 8, 9. And b vector minus 3, 4, minus 6. So if I want to compute the following, 2u minus 3v. Wait, no. Sorry, I want to have this same as in my notes. 3u minus 2v. Now, this is called a linear combination. You've heard a term, well, you will have heard a term if you take linear algebra, of u and v. A linear combination just means you're taking vectors and you're multiplying each one by some scalar, and then you're adding them up. So in this case, I'm multiplying u by 3, multiplying v by minus 2, and adding them up. So I can work this out in terms of the components of u and v. So I'd have 3 times the vector 7 minus 8, 9, minus 2v, so minus 2, minus 3, 4, minus 6. In the notes, I actually deal with components individually, but after do the addition first, but I'm gonna do the scaling first. So 3 times 7 minus 8, 9 would be 21 minus 24, 7. And then I have minus, and I'll take the 2 and distribute it through all the components here. So we have minus 6, 8, minus 12. So then you go ahead and carry out the subtraction of corresponding components. We have 21 minus a minus 6. So 27, and then we have minus 24 minus 8. Something off in my notes here. Okay, or there's a mistake somewhere. Okay, yeah, it's gotta be my notes. So I have minus 24 minus 8 is minus 32. And then 27 minus a minus 12, so 27 plus 12 is 39. In the notes I have minus 30 there for that y component, but I'm pretty sure that's wrong. Okay. Wow. Must have been smoking the good stuff back then. Kidding, I've actually never smoked a thing in my life, so. Okay. Okay. So questions about how we work scale and add vectors in terms of components. Things work out nicely for a change. Okay. Okay. Oh, right. Okay. Now, way of writing these vectors using the angle brackets and listing in components, that's one way of writing a vector, but there's another way of writing a vector that you may have seen, especially if you have taken any physics class. Make sure you're familiar with that too. Okay. So the vector space V3, so this is a set of all three-dimensional vectors. That's what I call the standard basis vectors. They're vectors that have first has components 1, 0, 0. So this is a vector that's pointing in a direction of positive x-axis. And then 0, 1, 0, that's pointing in the direction of a positive y-axis. And then 0, 0, 1, that's pointing in the direction of positive z-axis.
Is it?
Well, also they are unit vectors, but I'll talk about that. Now, can you tell me how these vectors are commonly labeled?
That's.
In the linear algebra community, yes. Unfortunately, it's not a linear algebra class. So that's actually what I prefer to use.
It's
But
oh,
don't say something in the chat.
Oh yeah.
Oh, I think my volume is low. Oh yeah, my volume was low. Repeat.
It's I hat, K hat, and J hat.
Yeah. Is that what you're doing? Oh, somebody. Okay. Oh, is that what you're saying too? Or, okay. Yeah, IJK. Often with the hat, where we have the hat, it depends on, I'm gonna put the hat here to distinguish from the ordinary letters IJK. In the notes, I have IJK without a hat, but they're bold. Or sometimes people might put the vector arrow on top of them. Okay, some sort of designation like that. IJK, or as vectors, but yes, these are also known as E1, E2, E3, the columns of the 3x3 identity matrix. Okay. All right, so it's common practice for some to express vectors in terms of ijk. So if I have a generic vector v that has components v1, v2, v3, that can be written as v1i plus v2j plus v3k. Or it's assigning the x, y, and z components to I, j, and k respectively. And this is for 3 dimensions. If we were in 2 dimensions, we would just have I and j. And we would drop the third component. That would be 0 anyway. Okay, so all the usual laws of addition apply. So suppose I have the vector u, 2 minus 1, 3. The its vector of components minus 4, 5, 0. So u would be 2i minus j plus 3k, and v would be minus 4i plus 5j, and there's no k because the z component is 0. So then, if I wanted to compute the sum, u plus v, I would look at first any I vectors and I'd add their coefficients together. So I'd have 2 minus 4 times I plus minus 1 plus 5 j, and then I only have 3k. Okay. Very good. All right. That's minus 2i plus 4j plus 3k. You know what it is in homework sets in math classes how they'll throw all the different kinds of notation at you. Like for instance, ODEs that are in terms of x, but then t, and then, yeah. So here again, because mathematicians can never agree on notation. Okay. Final good stopping point. Okay. Orange coming soon. Right. Now, as I mentioned, a vector has magnitude and direction. Now we know how to compute the magnitude of the vector, but it'd be nice to be able to have just the direction. So given a vector v, and they're going to assume that v is not the 0 vector. I define a vector u to be equal to v scaled by 1 over its magnitude. Then u is said to be a unit vector. And it's called a unit vector because the magnitude of u is equal to 1. Because if I take the magnitude of u, then that's equal to the magnitude of v from the numerator, and I'm dividing by the magnitude of v, and I get 1. But this particular unit vector is pointing in the same direction as v. And this process of taking a vector and dividing by its magnitude Yes, what I'm doing here is normalizing. No, not you, B. B is what's being normalized to get U. Anytime you're dividing a vector by its magnitude, you are normalizing it. It's going to get a unit vector. And there are a lot of cases where it's desirable to have a unit vector for one reason or another. Some things like that come up in Cal 4, for instance. Okay. So, a couple examples, involving unit vectors. And let V be the vector 3, -4, and 5. So then I go ahead and compute the magnitude of that vector. So that'd be 3 squared plus 4 squared plus 5 squared, so 9. So square root of 50 is the magnitude, which can also be written as 5 times the square root of 2. So then what I can do is if I divide B by this magnitude, then I get a unit vector. So 3 divided by 5 root 2 minus 4 divided by 5 root 2, then 5 divided by 5 root 2. That is the normalization of V. So U, which has a magnitude of just 1, that describes the directions that V is pointing in.
So is V divided by the magnitude of V called the norm of V, or is that?
No, actually, norm there's not a term I use in this class, but norm is often referred to is referred to the magnitude itself. Like I say, the magnitude of V, if like V, is also the norm of V. Yeah, that's one thing to be careful about. Yeah. But there are different kinds of norms, different ways of measuring magnitude of a vector. In this class, we just use this one, where we take what's called the Euclidean length of a vector, like the distance in Euclidean space from the terminal initial point to the terminal. But for instance, it's reasonable to describe the magnitude of a vector as taking the absolute value of its largest component. That's called the infinity norm. But I guess I'm getting into that. Okay. All right. Last example for today. And I'll have a little more vector material on a Monday, followed by cupcakes. We have the same attendance that we do today. You all getting a lot of cupcakes each. Okay. Now, all right, so my vector B is 2, 4, 5, 3. Okay, so I have to define C be a vector that has these properties: the magnitude of 5 and the direction is opposite of V. So the goal here is to figure out what C actually is. So the first thing that we do is we normalize V. get a hold of that direction. All right, so we get the magnitude of V. The square root of 2 squared plus 4 squared plus 3 squared, so that's square root of 29. Again, numbers don't work out nicely. Not every vector is going to be a Pythagorean triple. Okay, and so then we divide V by that magnitude. So we get a unit vector in the same direction as V. That's going to be 2 over square root of 29. 4 over square root of 29, and then minus 3 over square root of 29. Okay. So to get from U to Z, first we deal with direction. We want the opposite direction of V, so we negate it. And then to make sure it has the right magnitude, U has a magnitude of 1. And if we change its sign, it's still going to have a magnitude of 1. So to make sure that's a magnitude of 5, we scale by 5. In other words, Z is equal to minus 5 times U. So we get minus 10 over square root of 29, minus 20 over square root of 29, and then plus 15 over square root of 29. And wow, it does agree with my notes. Okay. Okay. I see this W in my notes, like, what is that? Oh, because in my notes, I don't have V, I have W. But everything's correct. All the numbers are anyway, so. Okay, so I think it's a homework problem like this, or possibly a problem on a test too, or like a little final exam where both the find a vector that has a given direction relative to some other vector, like pointing in the same direction or pointing in the opposite direction, and then having a certain magnitude. So, so by normalizing the original vector, then you can give it whatever direction or magnitude you need. Any questions about either of these examples? Well, nicer than sequences than series, isn't it? So, I think it's on the rest of the semester. Okay. And I know it's early, but I don't care. It's a logical stopping point. Then we cover the whole section today. All right. So Monday. I'll hang around in case anyone does have any questions.